Our HABC team took inspiration from Colonel Kittinger's high-altitude experiments. They inspired us to consider how would solid epinephrine, a life-saving drug for allergic reactions, behave in high-altitude atmospheric conditions. EpiPens, which use liquid epinephrine, are vital for over 3.6 million people in the US alone. However, in space, liquid epinephrine has a serious problem. It can turn toxic, risking lives. So, we set out to investigate if solid epinephrine could be a safer, more sustainable alternative. We hypothesized that it would not remain stable under harsh, high-altitude atmospheric conditions. We firmly believe that additional solid epinephrine research could transform medical safety for future military and commercial space missions.
The potential benefits of solid epinephrine are very clear in assisting future space workers with their physical health. However, much more research must be done to determine the most effective and cost-efficient ways to transport, store, and administer this medication in a space environment. Our findings lead us to believe that solid epinephrine may reduce the likelihood of degradation in toxic compounds, thereby making it safer for use in space, increase shelf life, which is essential for long-distance space missions, simplify storage and transport by taking up less space and weight, which is a critical consideration in space travel. Our consultation with experts strengthened our belief in our results. Our thanks go to Professor Mayer at the University of Ottawa, who led the team that conducted the EpiPen experiment in Canada, Dr. Lenhart, a NASA space medicine expert who helped us understand the value and applicability of our experiment, and Dr. Gurgis at George Mason University at the Bioengineering Department, who helped us conduct and validate our scientific analysis.
For several weeks leading up to the experiment, our team focused on possible methods of testing our epinephrine sample for changes. Due to significant shipping problems that impacted our ability to obtain sufficiently large epinephrine samples, our team explored alternative testing methods. Additionally, a medical professor advised us not to directly handle the epinephrine. Therefore, we had to devise an alternate method of filling our flight capsules.
After considering many intriguing alternatives, we decided to evaluate how solid powdered epinephrine or epinephrine bitartrate would be affected at the molecular level by high-altitude atmospheric conditions. During our research, we learned that a similar experimental protocol had been performed in 2023 by a Canadian team using the liquid form of epinephrine. In order to receive precise results in our experiment, we used a liquid chromatography mass spectrometry machine, or LCMS, at George Mason University with the assistance of Dr. Gurgis.
Based on the feedback from experienced professionals and our team's extensive research, we are confident that our data is accurate within the bounds of our experiment. Dr. Lenhart from NASA provided us with insights into space medicine. Dr. Gurgis from the George Mason Biotechnology Lab granted us access to his lab and shared his expertise on what affects solid organic compounds such as epinephrine. Dr. Mayer's previous research on the effects of high altitudes on liquid epinephrine gave us a roadmap of possible methods to collect our data. One crucial piece of information we discovered, which affects our experiment directly, is the presence of sodium metabisulfite in EpiPens, also known as liquid epinephrine. Sodium metabisulfite is used as a liquefying agent in EpiPens and will decompose and become toxic in high temperatures greater than 150 degrees Celsius and when in contact with water. Our initial hypothesis was refined to incorporate the information we gathered from our research and the advice from Dr. Lenhart and Dr. Mayer. Once we analyzed our data, we concluded that the high altitude conditions did not affect the epinephrine. By overlaying the graphs of mass overcharge versus the number of ions, we could see that there was no significant difference between the two control capsules and the two flight capsules of epinephrine.
Our team learned the scientific process required to running our experiments. We also learned the skills necessary to communicate with scientific professionals. As a result of our work, we determined there was no significant difference between the epinephrine of the flight and control capsules. Were we to continue with our work with the epinephrine protocol, we would re-execute our experiment using the same samples as the Canadian team. We would expose our epinephrine directly to radiation for several hours and see if there was any change.
One of the most likely reasons that our flight and control capsule test samples had nearly identical results was that there was no effect on the solid epinephrine from the high-altitude atmospheric conditions. However, another possibility that our team and the professor explored was that an inorganic compound in the epinephrine changed that the liquid mass spectrometry machine couldn't measure.
Working together as a team in HABC has been extremely rewarding and a great scientific learning experience. If we are awarded any prize money, we would dedicate a large portion of it to future HABC experiments. We will also formally recognize those who assisted us with certificates of appreciation. We would like to thank Compass Homeschool for their facilities and Dr. Lenhart from NASA for his expertise in extreme medicine. Finally, we are extremely grateful to Dr. Gurgis from George Mason Biotechnology Lab for letting us use the liquid mass spectrometry machine.